Hello everyone. Today I am Rishabh Bhardwaj, Assistant Professor from Mechanical Department, taking the lecture of heat transfer. Today in this lecture we will discuss about thermal and hydrodynamic boundary layers and equation of continuity. Let's start with this thermal boundary layer. Here we can see we have a two coordinate. In the two coordinate we have just made a diagram by which it is showing the flow. In the initial point we have a laminar flow where the Reynolds number is less than 2000, and then we have a turbulent flow where the Reynolds number is more than 4000. Meanwhile, it is the region affected by the heating, and below that we have a plate surface which is a heated region, and the above curve shows the thermal boundary layer, and we have the another limit of the thermal boundary layers. It is a flow of cool fluid over a warm plate. Uh, some parameter used to characterize the property of thermal boundary layer formed by heating fluid or moving along the heated wall. In many ways, the thermal boundary layer describes parallel the velocity boundary layer. Description first, conceptualized by the pendant. For this, we have to consider a uniform temperature, that is a T naught, and the velocity U naught, impinging on the stationary plate uniform heated with a temperature Ts. Assumes the flow and the plate are semi-infinite in the positive or negative direction, perpendicular to the xy plane. As the fluid flow along the wall, the fluid at the wall surface sacrifices no slip boundary condition and has zero velocity. But as you move away from the wall, the velocity of the flow symbiotically approaches the free stream velocity. The temperature at solid valve is Ts and gradually changes to T naught as one moves towards the free stream of the fluid. It is impossible to define a sharp point at which the thermal boundary layer fluid or velocity boundary layer fluid becomes the free stream. Yet this layer have well-defined characteristic thickness given by del T and del V. The parameters provide a useful definition of the characteristic measurable thickness of the thermal boundary layer, and also include in this boundary layer description are some parameter useful in describing the shape of the thermal boundary layer. If we discuss about the 99% thermal boundary thickness, the thermal boundary thickness, that is the del T, is the distance across a boundary layer from the wall to the point where the flow temperature has essentially reached the free stream. The temperature T naught. This distance is defined normal to the wall in the y direction. The thermal boundary layer thickness is customarily defined as the point in the boundary layer where y with the suffix 99, where the temperature T, the coordinate of x and y reaches 99% of free stream value of T naught. At the position X along the valve in the real fluid, this quantity can be estimated by measuring the temperature profile at a position X along the valve. The temperature profile is the temperature as the function of Y at the fixed position X. For the laminar flow over a flat plate at zero incidence, the thermal boundary layer thickness is del T is equal to del V Prandtl number raised to power minus 1 by 3. For the turbulent flow over a flat plate, the thickness of the thermal boundary layer is not determined by thermal diffusion, but instead it is random fluctuation in the outer region of the boundary layer of the fluid that is driving force determining thermal boundary layer thickness. Thus, the thermal boundary layer thickness for turbulent flow does not depend upon Prandtl number but instead on Reynolds number. Hence, the turbulent thermal boundary layer thickness is given approximately by the turbulent velocity boundary layer thickness. The turbulent boundary layer thickness formulate the flow is right from the start of the boundary layer. The turbulent boundary layer behaves a geometrical similar manner, and it is neither one of these assumption is true for the general turbulence boundary layer. So the case care must be exercised in applying the formula. Then we will discuss about the thermal displacement thickness. The thermal displacement thickness may be thrown off in terms of the difference between the real fluid and hypothetical fluid with thermal diffusion, turned off with velocity u0 and the temperature T0. With no thermal diffusion, the temperature drop is abort. The thermal displacement thickness is the distance by which the hypopotential or hypothetical fluid surface would have to move in the y direction to give the same integral temperature as occurred between the valve and reference plane at del T in the real fluid. It is a direct and analog to the velocity displacement thickness, which is often described in terms of equivalent shift of hypothetical fluid, and the definition of the thermal displacement thickness for incompressible flow is based on the integral of reduced temperature. Next we will move to the hydrodynamic boundary layer. For the hydrodynamic boundary layer, we have a leading edge which is heated and air is blown over the surface. Here we in the initial state that will be form a laminar flow when there is no slip will be taken at the initial point, and the velocity will remain increasing below the velocity or Reynolds number below 2000. A laminar flow will be formed, and above the Reynolds number more than 4000, the turbulent flow will will be seen. In between 2000 and 4000, there is a transition flow. Here in the laminar flow, the limit has to be taken as 3 into 10 raised to power 5, and for the laminar flow, for the turbulence flow starting, that has been taken at 5.5 into 10 raised to power 5. Then we have a laminar sub layer available just above the flat plate. The free stream undisturbed flow has a uniform velocity u infinity in the x direction. The particles of fluid adhere to the plate surface as they approach it, and the fluid is slowed down considerably. The fluid become stagnant and virtually so in the intermediate vicinity of the plate surface. Generally, it is pre-assumed that there is no slip between the fluid and the solid boundary. Thus, there exists a region where the flow velocity changes that of solid boundary to that of mainstream fluid, and in the region of velocity, gradient exists in the fluid. Consequently, the flow is rotational and shear stress are present. This thin layer of changing velocity has been called the thermodynamic boundary layer. The condition del u by del y is not equal to 0 is true for the zone within the boundary layer, while the condition for flow beyond the boundary layer and its outer edge are del u by del y is equal to 0. Thus, all the variation in fluid velocity is considered in a comparatively thin layer in intermediate vicinity of the plate surface. The concept of boundary layer thickness and outer edge of the boundary layer are quite fictitious, as there is no abrupt transition from the boundary layer to the flow beyond the outstate. Velocity within the boundary layer approaches the free stream velocity. Usually the boundary layer thickness and is taken to be the distance from the plate and the surface to the point at which the velocity is within 1% of the asymptotic limit, that is v is equal to 0.99 as shown in the figure. Then the thickness of the boundary layer is variable along the flow of the direction. It is 0 at the leading edge of the plate and increase the distance x from the leading edge is increased. This aspect may attributed to the viscous force which dissipate more and more energy of the fluid stream as the flow proceed. Consequently, a large group of fluid particle is slowed shown. The boundary layer growth is also governed by the parameter such as the magnitude of the incoming velocity and the kinematic velocity of the flowing fluid. For higher incoming velocity, there would be less time for viscous forces to act according to their less quantum or boundary layer thickness at a particular distance for the leading edge. Further, the boundary layer thickness is greater for the fluid with greater kinematic velocity. For some distance of the leading edge, the boundary layer is laminar and the velocity profile is parabolic in character. Flow within the laminar boundary is smooth and streamlines are essentially parallel to the plates. Subsequently, the laminar boundary layer becomes unstable and laminar flow undergoes a change in its flow. structure at the certain point called as transition point in the flow field, where the transition zone the flow is unstable and refers to a transition flow. After going through a transition zone to infinite length, the boundary layer entirely changes to turbulent flow boundary layer. The turbulent boundary layer does not extend to the solid surface. It is extremely thin layer called laminar sublayer and is formed wherein the flow is essential for laminar character. Outside the boundary layer, the main fluid may be either laminar or turbulent. The pattern of flow in the boundary layer is judged by the Reynolds number, where the x is the distance along the plate and measure from its leading edge. The transition from laminar to turbulent pattern to the flow occurs at value of Reynolds number within between 3 into 10 raised to power 5 to 5 into 10 raised to power 5. Beside its critical Reynolds number, the coordinate number at which the laminar layer begins and stabilized turbulent flow set in dependent on surface roughness and plane curvature and the pressure gradient, the intensity of turbulence of free stream flow. In the laminar boundary layer, the velocity gradient becomes less steep as one proceeds along the flow. It is because now the change in velocity from no slip at the plate surface to free stream value in the potential core occurs over a greater transfer distance. Nevertheless, in turbulent boundary layer, there occur an interchange of momentum and energy amongst the individual layer comprises the boundary layer, and consequently a turbulent boundary layer has a fuller velocity profile and much steeper velocity gradient at the plate surface as compare or when compared to one laminar boundary layer. The velocity gradient and hence there the shear stress has a higher value of plate surface. For a laminar boundary layer, the velocity gradient becomes smaller along the flow direction and so does the shear stress. However, the turbulent boundary layer, the shear stress has a plate surface again takes up a high value consistent with the stepper velocity gradient. The development of boundary layer for pipe flow proceed in a fashion similar to that for flow along a flat plate. However, boundary layer is limited to the pipe radius because of the flow being within confined passage. Boundary layer from the pipe wall meet at the center of the pipe and entire flow acquires the characteristic of the boundary layer. Beyond this the point the velocity profile does not change and it is said to consequently a fully developed flow. And the further the velocity gradient and the wall stress are greatest at the pipe entrance and drop to the steady value and the beyond the region of fully developed flow. The characteristic velocity distribution of fully developed and laminar and turbulent boundary layer flow inside a pipe are depicted. For the boundary layer, then we have the boundary layer thickness is taken to be distance from the plate surface to the point at which the velocity is 1% of its limit. And the local skin friction, that the coefficient, refers to the ratio of local wall stress to the dynamic pressure of the uniform flow. Let's next move to the our next topic, that is equation of continuity. For this we have considered a cuboid which having a side dx, dy and dz. In this equation we will consider several components or the terminologies. That could be the rho, that stands for the mass density of the fluid at a particular distance, and UVW, that are the component of the velocity of flow entering the three faces of the parallelopiped. Initially, let's start with the rate of flow, the rate of mass fluid entering the phase from A, B, C, D. First, we consider the phase, that is A, B, C, D, where the mass is and the mass fluid is entering. That will be the rho into the velocity into the area of ABCD. That will imply that rho is the density and velocity in the x direction is u, and the area is dy into dz, where the mass of the fluid leaves at the phase, that is a EFGH, where density into u into dy into dz plus the mass that leaving from EFGH, that will be curl rho u dy dz into dx with respect to curl x. The gain in mass per unit time due to the flow in the x direction is given by the difference between the fluid influx and fluid efflux. The mass accumulated here per unit time due to the flow of x direction. If we adding both, then we will get a result that will be the minus curl rho u dx dy dz and with respect to curl x, where the dx dy dz are the components of the direction and it implies the value, that will be the volume. Similarly, the gain in fluid mass per unit time in the parallelopiped due to the flow y and the x direction are like curl rho v dy dz and dx, and for the x direction, for the z direction, that curl rho w dx dy dz by curl z. The total gain in fluid mass per unit time for the fluid flow along the three coordinates, that the three coordinates, that x, y and z. Then we will add the three of these equation, that will be curl u by curl of rho u by curl x plus curl rho v by curl y plus curl rho w by curl z into the dx, dy and dz. The rate of change of mass of parallelopiped control volume, that will be curl rho dx, dy, dz by curl time. From this equation, combinedly we have evaluating by putting to the right hand side and get that curl rho u by curl x plus curl rho v by curl y plus curl rho w by curl z into curl rho by curl t is equal to the 0. This equation is the general equation of continuity in 3 dimension and is applicable to any type of flow and for any fluid, whether compressible or incompressible. For the steady flow, now we are considering the some conditions over there, and for the steady flow, curl rho by curl T will be the 0. For incompressible fluids, the density, that is rho, is constant, and the equation reduces to curl U by curl X plus curl V by curl Y plus curl W by curl Z is equal to the 0. And for the two-dimensional flow, the equation will be the curl U by curl X plus curl V by curl Y is equal to 0. And condition for the one dimension only, the curl U by curl X is equal to the 0 has to be formed. When we integrate with respect to the X, the U is equal to the constant. And if the area of the flow is a rate of flow, then Q is equal to the AU and is equal to the constant for steady flow. Now we have the continuity equation for the polar coordinates. The equation of the continuity in polar coordinates for the compressible fluid can be taken as 1 by R rho V plus curl rho V R by curl R plus curl rho V theta by R curl theta is equal to 0. For the incompressible flow, the equation will reduce to VR by R plus rho curl VR by curl R plus curl V theta by R curl theta is equal to 0. Where curl R is the component of the radial direction and the V theta is the velocity component in the tangential direction. This is the equation of the continuity, where inlet and the outlet pressure or mass or energy will be the constant. For this session, I am saying thank you to all of you to watching this video, and stay tuned for the next. Thank you.